This is the second lecture from Math 107, Chapter 3. It is on the roots of polynomials. In the first lecture, I said that the degree of the polynomial is equal, or the number of roots of the polynomial is equal to the degree of the polynomial. Remember that the root is the value of x for which the polynomial is 0. Graphically, this means that the graph of the polynomial will cross the x-axis at one of the roots. So what I'm first going to do is show you a bunch of polynomials and count up the roots for you, try to give you an idea of what this means. Okay, so I'll start off with the simplest polynomial, and that is the polynomial of degree 0. Its degree is 0, so there are 0 roots. That's what I said the rule was. Okay, look at the graph. If the polynomial is equal to 5, then that is a horizontal line through y of 5. Okay, and it never crosses the x-axis. Of course, this is no proof, it's just a demonstration or an example. Now here's a polynomial of degree 1. Remember, degree is the highest value of the exponent in the equation. Well, of course, there's the invisible 1 right here, so that's why this is of degree 1. This is a linear equation. I've said that the rule is that if the degree is 1, there's one root. And if you plot a linear equation, there is only one point where the polynomial, in this case a straight line, crosses the x-axis. So degree 1, one root. And the turning points, the maximum number of turning points is 1 less than the degree. So the max, should say max here, maximum number of turning points would be 1 minus 1, which is 0. So here's a polynomial of degree 2. We said it had 2 roots. Of course, there's some complications concerning these 2 roots, but essentially it has 2 roots. And for this polynomial, you see there's 2 points, minus 1.75 and 1, where this polynomial crosses the x-axis. Those are the 2 roots of the polynomial. It's a quadratic function, and so it's sort of, you expect this. Now, when we had the quadratic functions, we called either the lowest point or the highest point, which was halfway between the 2 roots, of course, we call that the vertex. That term is unique for quadratic functions. When you talk about polynomials in general, you would call that point a turning point. And the maximum number of turning points is 1 less than the degree, so the degree is 2, so the maximum number of turning points is 1, and here we do see 1 turning point. As a function comes through one x-axis crossing, turns around, and goes through again through the next x-axis crossing. How do you find the roots of a polynomial? You set the polynomial equal to 0, and when you have the quadratic function, decided not to write a 0 there. Okay, well, I'll put the 0 over here. If you have a quadratic function, you can use 3 tools. You can factor the polynomial, you can complete the square, or you can use the quadratic formula. When you get into higher order polynomials, I use order and degree sort of interchangeably here. When you get to higher order polynomials, you don't have those tricks available to you. We will study in the next couple lectures a few of the techniques that you can do to maybe find a root or 2, or at least to get close to them. Okay, so for review, this is a polynomial of degree 2. It has 2 roots, and the number of turning points, the maximum number of turning points, is 1. So moving right along to a polynomial of degree 3. It's of degree 3 because the exponent, the highest exponent is 3. Right? It's a cube, x cubed, so it's degree 3. The number of roots is 3, and the maximum, left off max on these slides, maximum number of turning points is 3 minus 1, so it's 2. And here we see our 3 roots, 3 places where this graph is crossing the x-axis. And now the turning points, here's one turning point right here, and here's another turning point there. And this graph does indeed have the maximum number of turning points 2, and you're seeing the 3 roots. Here are the roots, minus 4.3, minus 0.7, and plus 1/2. And now here's one more example, a polynomial of degree 4. We expect 4 roots. and here they are, minus 4, minus 3, 2, and 5. The maximum number of turning points is 4 minus 1, which is 3. In this case, we do have the 3, the maximum number of turning points. How do you find these? Well, if you knew them, and you could find them by a computer, maybe, or you could factor it, you would end up being able to write it in this factored form, and you can pick off the roots like that. And we'll discuss how to do that a little bit later. So right now, the whole idea of these graphs is for you to get used to seeing what is a root, be able to pick it out graphically, and have some kind of feel for what you're looking, what you're doing the algebra for. Now recall from the quadratic function, what kind of roots could you have there? You could have 2, because you expect 2 roots, it's a polynomial of degree 2. You could have 2 distinct real roots. Remember this? I think the C belonged here. Okay, 2 distinct real roots, like 4 and 6 or something like that. You could have 2 equal real roots. Or you could have a complex conjugate pair. Again, 2. This same idea goes forward into polynomials of higher order or higher degree. All the roots, for example, if you have a function, a polynomial of degree 6, you could have 6 distinct real roots. On the other hand, some of those roots could have the same value. So to express that, if the value of the root is repeated, we count up the number of times it's repeated, and we call that the multiplicity. If you were in quadratic equation, and you had a 2 equal real roots, and say they had the value 5, then you say the root has a value 5 with a multiplicity of 2. So you use this word multiplicity. Again, like I said, a lot of this polynomial study is terminology. So it's multiplicity. If you had a polynomial of degree 6, and every single one of the roots had the value 10, then you'd say the value of the root is 10 with a multiplicity of 6. You just count up the number of times that it is repeated. The second point, if there is a complex root, there's also going to be its complex conjugate. The complex roots will always occur in pairs, and they will be complex conjugates. The graphs look a little bit different. In fact, you have fewer turning points when you have a multiplicity. Here's an example. This is a polynomial of degree 3. To find the roots, we set this equal to 0, and we factor what we can. In this case, we could factor out an x squared, and we're left with x minus 2. We're setting each factor to 0. This term will give us the root of 2, which you see right here. But x squared equals to 0 will have 2 roots. They will both have the value 0, so you have a root of 0 with a multiplicity of 2. When you have a root with a multiplicity, instead of crossing over the x-axis like this, the graph will come up to it, approach it, and hit the x-axis at that point, and then turn away from it. In this case, you still have 2 turning points, but if you had a higher order polynomial with a higher multiplicity, you would lose those number of turning points. You would not achieve the maximum number of turning points, which in this case, of course, is 2. So that's basically the idea with some examples, some graphs there. So hopefully that you have that in mind, what a root is. You're looking for a value of x for which a polynomial is 0. When you think of it in terms of a graph, it is the value of x where the polynomial either crosses the graph, or at least comes up, crosses the x-axis, or comes up and touches the x-axis in one point. And that's what we're going to be looking at for the rest of this chapter for polynomials. We're looking for the roots of the polynomials. Now we're going to start off by using some theorems, and I want to give you a little framework or a little point of reference for what theorems mean. I'm going to contrast it with science here because we're more familiar with science, perhaps. In science, you have laws, like Maxwell's equations, considered laws for electricity and magnetism. You have law of gravity, entropy. You have these various laws of physics. Now, when you work in physics or science of any kind, engineering, you come up with inventions. And there's two things that the invention has to do. First, it has to work right, and then it cannot violate the laws of physics. There's always stories of people turning in inventions to the patent office that are perpetual motion machines. Well, that violates the idea of, or the law of, the conservation of energy, and so whether that invention appears to work or not, because it violates the law, it is thrown out. Right? So now when we move to math, we don't use the word law and invention anymore. Instead of law, we use the word axiom. And here's our equivalent in math to the word law. Now, do the laws change in science? Do they get enlarged? Yes. And it's generally people who are very famous and illustrious and quite gifted in science or math that mess around with the laws or the axioms. Most people, of course, stick with inventions and theorems and are happy with that. So when we move to an invention in science, when we're in math, we move to what's called the theorem. A theorem is similar to an invention in science, and it has the same kind of requirements on it that the invention did. The theorem cannot violate the axioms, and you have to prove that it's true. Proving something is true is often very difficult. It's easy to prove something is false. All you need is one counterexample, and that's it. Now, if you have a theorem you're trying to show and you show me 10 examples, you still haven't proved it, because there might be lurking out there that 11th example that totally disproves your theorem. So there's a lot of work done in proving theorems. In fact, they have classes in math departments just to help you learn how to prove things. At the end of this chapter, into this semester, we're going to do Chapter 7 before Chapter 6, and in Chapter 7 is discussed proof by induction. It's one method of proving that a theorem is true. Okay, so with this terminology in mind, now you sort of know, I hope, a little bit better what a theorem is. So now I'm going to show you the theorems that we're going to use to prove that these roots do exist and get some idea on how to find them. At this point, I'm just going to give you the names just so you can kind of see how these are going to sort out. We said already that if the polynomial is of degree n, it has n roots, and I showed you some pictures which made you think, yeah, that's probably true. But we need to do a little bit better than that, and there are 4 theorems that work up to showing you that if the polynomial is of degree 5, it has 5 roots. They might not all be distinct. You might have complex conjugate pairs in there, but there will be 5 roots. And here are the theorems. We start with the remainder theorem and move to the factor theorem. Oh, that was supposed to be a marker, sorry. Okay, so we start with the remainder theorem, then we move to the factor theorem, and those are more demonstrated than proved. And the fundamental theorem of algebra is stated. Again, it's not proved, but you will see how these things progress. And then from the fundamental theorem of algebra, it's immediate that you can achieve the polynomial factorization theorem. At that point, we can say we proved that if the polynomial is of degree n, it has n roots. Now the question is how to find the roots or estimate them. If we have the quadratic function, we have certain tools. If we have a linear function, all we have to do is isolate x, set y equal to 0 and isolate x. For the quadratic function, again, we have the quadratic formula, completing the square, or factoring. But when it comes to higher order polynomials, we do not have those kind of tools available. And this is what we have. We have Descartes' rule of signs, which shows us how many positive and how many negative and how many complex roots we might have, different combinations of them. Then we have the rational root theorem, which actually helps us to find some of the roots if possible. And the third is the intermediate value theorem. By using the intermediate value theorem, you can write an algorithm on a computer that will help you find the roots. And this is how the roots of most polynomials are found, using the intermediate value theorem, or what's called the bisector method that's developed from that, or some other more advanced method.